So we've seen 5 or more examples of specific curves and their parametric equations, their parameterizations. In this video, we're going to generalize these special cases that we've looked at. So in general, there are 2 ways that are equivalent for representing a curve. Parametric form, we can give the x, y, and z coordinates as functions of t. So x equals x of t, y equals y of t, z equals z of t. So think about just giving the coordinates of a particle that's moving through space. If t goes from a to b, then we are starting at the point x of a, y of a, z of a, and then after a little bit at t1, we get to our first point. After t2, we're getting to the second point. And so in this way, we can describe our particle as it moves along all the way from the starting point to the ending point for t from a to b. The second way to describe the same curve is in vector form by describing, given an expression for the vector from the origin to the point that our particle is at. So for our starting point, we would get the vector right here. So the vector r of a. And then for our first point along the way, we have r, and now we plugged in t1. And for each of these points, we can draw in the vector describing also the position of our particle. And so the last one would be the vector pointing over here. I'm going to draw that in as a dotted line. Over here, that would be r of b. This is in general for any curve. And then we saw a few specific cases. We saw how to parameterize circles. And here I'm just giving the example of a circle of radius r in the xy plane centered at a comma b, and it's traversed only once. This could easily be extended to equations for circles in 3 dimensions. But so if you're just looking at a circle in 2 dimensions, we give the x coordinate as a plus r cosine t, y equals b plus r sine t. So again, this circle is centered at a comma b, and it has radius r. So you see where they show up in our equations. And if we want to move clockwise around this circle, we are using a plus r cosine t for x and b plus r sine t for y, and we let t go from 0 to 2 pi to go around the circle once. If we wanted to switch directions, all we would have to do is change the sign in front of sine t for y. So to go clockwise, we have x is equal to a plus r cosine t and y is equal to b minus r sine t. We also saw how to parameterize lines. And to describe a line using parametric equations, we need a starting point. Let's call that point x0, y0, z0. It can be any point on the line. And we need a vector that is parallel to the line. So let's call that vector v right here. And so our point P is x0, y0, z0. And then we are moving parallel to vector v. And we can describe this again in 2 different ways. If we want to describe the entire line, we can have x is equal to x0 plus at, y is equal to y0 plus bt, z is equal to z0 plus ct. And if we want the entire line, we'll just let t go from minus infinity to infinity. And so for positive values of t, we would get everything in this direction of p, and for t less than 0, we would get everything in the opposite direction. If we only want to parameterize part of this line, so just a line segment, in this case, let's look at the line segment that is given in the picture from P to R, then we are starting at x0, y0, z0. We still have the same equations. So we still have x is equal to x0 plus at, and we still have y is equal to y0 plus bt, and we have z is equal to z0 plus ct. But since we only want to go from the point P to the point Q, we are starting at the value t equals 0. And you can see if we plug in t equals 0, we would just get x0, y0, z0. And then we are stopping when we've arrived at R. And, well, what is R? R is the point that you get if you start at x0, y0, z0 and move along V. So you arrive when t is equal to 1. So that's how you get a line segment. For functions in the xy plane, we can also generalize how to describe the curve of a function. And this is a generalization of the two parabolas that we've seen in examples 3 and 4. So in general, if you have a curve that's given in terms of a function, y is equal to f of x, where x is the independent variable and y is the dependent variable, then you can describe every point on that curve through, in terms of t and f of t, starting at a and ending at t equals b. And so you can say x is always equal to t, and then y is always equal to f of t. And since we wanted to start at a, f of a, and end at b, f of b, we start by plugging in a, and we end by plugging in b for t. And again, these formulas can also be extended to give equations for functions of curves in